Okay, welcome everyone. Just last minute changes. I'm trying to sort of basically cover some leftovers that we have from last time. So I'll spend maybe 3 to 4 minutes just talking about the motion pathways which we discussed, and I did not quite finish last time. So just to give you sort of an overall picture, we were talking about, if you remember, neurons in the parietal cortex. So in the parietal cortex here, which get information from neurons in MT, which are the superior temporal sulcus, which are selective to the direction of motion, and they sum up the information so that there are these integrators that are relevant for decision. Are you going to make a saccade to the left or to the right? And we saw that there's they have a motor component to them, so that we mentioned that they are related to decision making. And we said that they, you can see that the stronger the motion signal, the higher the coherence of the random dots, the faster the increase you get in their firing rate. So this is motion in the preferred direction, that's in another direction. You see that if it's in the preferred direction, they fire strongly because the evidence, and they're accumulating evidence about the direction of motion with time. Okay, and the last thing I mentioned was that, okay, if we look at the response as the monkey is trained and getting better in performing the task, you see that their slope is increasing, meaning that their efficiency of accumulation of information gets better. And the question is, how do we understand that? Okay, how do we understand this better efficiency in accumulation of information? So there's 2 ways to understand this. Okay, so think about it, this sort of LIP neuron, which gets information from neurons in the preferred direction and in the null direction. And you remember, you have to compare the information from the neurons that are, let's say, sensitive to the upwards versus ones which are sensitive to downwards to decide if motion is upward or downward. Okay, and if the coherence is very, very low, then it's, you know, the information from both of this is somewhat limited and uninformative. And of course, you sort of, the way you do this is you integrate over time. So even if there's very low amount of coherence in the preferred direction, if you have the time to integrate information, then you are more likely to arrive at the right decision. So what these neurons do is are integrators. So this is the integration sign. They're integrating the information over time. And this is here described here as a change in the slope here. Okay, so the more sensitive the neuron is, the greater the slope, the better, the more efficient the integration of information across time. You may hear this also from Mati at some point, because he's sort of working on similar aspects. And the idea is, okay, how is this being done? Well, one way to think about it is to say, okay, that the change is actually occurring in MT neurons, but they're getting more sensitive. But that's not the case. So how can we understand this? Think about these empty neurons that are selective to, let's say, one direction, okay? Let's say 270 degrees plus or minus with some jitter between them. And you pull the information from all of these, okay? So one way to think about it is, here's this neuron, this integrator, which pulls information across these neurons. Well, how are you going to get this guy to be more efficient? Any ideas? So you're pulling information from these. Well, if you can see, each of them has a slightly different preferred direction, but also the standard deviation here is different for the neurons. Meaning that if you, on a trial-by-trial basis, the responses are not exactly the same, but there's some degree of noise in the response, okay? So of course, what's the best way to do is to give more weight to the more reliable neurons, okay? And how can you do this? So these are sort of the weights that are of how much weight is given to the firing of a neuron number 2 and 1 and so on and so forth. And you can see that, okay, number 2 is, its signal to noise in terms of the peak firing rate versus the standard deviation is better, for instance, than number 3. So let's give more weight to number 2 at the expense of reducing the weight of number 3. And this way we're going to have this integrator here is going to be more selective to the motion signal from these cells. So that's one idea. Another, which I haven't mentioned, but is related to my last talk. So remember we talked about correlated signal and correlated noise? Well, remember what we said was the limiting factor for the integration? Just to sort of remind you, we probably don't remember, but we were talking about this, remember? So we said, okay, here's the idea again. You have a sort of a decision based on a pool of the information from the up neurons and the down neurons, and you compare the two, right? And we said, what's limiting the sort of the information is the signal to noise ratio, right? Which is sort of due to the correlation between the neurons. So the more correlated they are, the more limit you have in the sense that you reach an asymptote at a lower signal to noise ratio. So one idea you could do is to think about not just giving more weight to the more sensitive neurons, but actually to change the degree of noise correlation between the neurons. So neurons that signal the same direction, you want to decorrelate them as much as possible. So that's another idea that I'm just sticking in your mind of how you can get to these neurons in LIP who are summing the information to be more effective in deciding if the motion was upwards or downwards. Okay, so that was just leftovers from my last talk, and I'll be very brief and give you 5 minutes sort of an introduction for our theme today. And so the theme today is going to be on the ventral stream and really related to visual object recognition. And we're going to hear two talks about aspects related to visual object recognition, but I just want to sort of put the general sort of frame of what's the problem. And the problem, one can understand it as the following. Say you have an image here. Well, what we talked in our last lectures was about what's happening in early visual cortex, mainly in V1. We said, okay, you have these neurons which are selective to contours here. So you get basically, if you think of primary visual cortex, you get maybe edge detection. So you get these different edges, and neurons that are sensitive to the edges in different locations on the in the image. Okay, so you get a contour map. But how do you know, okay, now from this contour, what belongs to an image and what not? Now, it seems so trivial that, okay, this is one subject here, but you think about it, you can think, okay, maybe the contours you should pay attention to are these, okay? And we immediately can sort of segregate different objects here and segregate the scene into different objects. But of course, the contour map is essential, but it's not enough, okay? So there's a lot left beyond V1, which we talked about, you know, doing edge detection or sort of Fourier analysis. I gave that aspect as well. So want us to think about this in terms of sort of levels of vision. So you know, the initial level of vision, which is somewhat related to V1, is that you have different cues, such as motion cues and luminance-defined cues and so on and so forth, in which you extract contours, okay? And you do something about boundary assessment. But you need to continue and sort of to extract using what's called intermediate level vision, something about other cues such as shading or texture and motion or occlusion relationships to understand something about 3D surfaces, okay? And from there, you want to basically finally get something about, you know, you want to understand where are the objects in the scene and so on and so forth. So there's one can think of sort of a vision as, you know, something, a cascade going from very early vision, which you basically get just boundaries and contours and boundaries, to understanding what the scene is. And of course, there's a lot of feedback going from higher level areas that can affect processing also in the intermediate and low level vision, such as visual attention. We don't have time to get into that, but that's one major way in which you can impact processing already at the early areas. So, and now if you think about the physiology of this, then when we talked about information going from the retina to the LGA and arriving in V1, we talked a bit about processing in MT, and now we're going to talk about the ventral stream, which is related to object recognition, and that's just to give you sort of an idea. So there's two trees, you know, the ventral one and the dorsal one going up to parietal cortex, and we're focusing now, today we're going to focus on the ventral stream. That just gives you some numbers, okay, in terms of how big are these different areas. So V1, you see there's like 37 million neurons in V1, and the timing in which the first response, and the timing in which response starts. So the V1 starts firing at about 50 milliseconds from the time that you present the image, and as you move up in the hierarchy, the first wave arrives in the IT infratemporal cortex, which we're going to discuss today, at about 80 to 100 milliseconds of after stimulus onset. Now, of course, once you get activation, so the first wave of activation is strictly bottom up, okay? But later you get now start sort of reverberations in each area, and also feedback going from these higher order areas to lower areas, which impact also processing in the early visual cortex. And that's just another way to describe it, okay? Here's the timing here. So the colored areas are the ones which are active first. You see V1 empty. Empty is actually an area which is activated very fast. And then as you move here, you see that there's recruitment of more and more areas. So you see that this is going into, we were talking about parietal cortex 7A, that's the next, and MST, which is sort of another motion processing area. We didn't get to talk about that too much. And then you see basically how sort of you get activation sort of feeding into more and more areas. So here's the ventral stream. So you see, okay, that the areas in the ventral stream are activated later compared to MT and some of the dorsal areas, and that's just sort of the timing of this. And here you get sort of a brief summary in which you can see that, okay, if you're talking about V1 neurons, they're selective to orientation. We talked about this, maybe spatial frequencies also. And as you're moving, the receptor field of the neurons become bigger, okay? So if you watch here, here's the receptor field of the neurons in V1. They're typically 1 degree or less, depending if they're in the center or in the periphery. And as you're moving up in the hierarchy, the receptor fields get bigger. And also, the complexity of the stimulus, which best drives the neurons, becomes more and more complex. Okay, so that's just to get an idea. And since I promised that I will finish in 50 minutes, I have 2 more minutes. That's just to give you an idea. Here's a neuron that you record from IT. Okay, that's deep in the ventral stream. And just to make things complicated, you see that some people call this TO and TE, and others call this posterior, central, and anterior IT. It's just the same areas, just different people have sort of placed their flag on the Everest and called it a different name, so it'll be their name, okay? So don't get this, don't mistake the same areas that we're talking about, posterior and anterior IT, being TO and TE. So here's one example of a neuron which is recorded here just to give you sort of, so it's a raster showing you the response to different stimuli that they've used, okay? And basically, what I want to make is, okay, there's no clear sort of tuning. If we were talking about empty neurons, right, we were talking about the neurons sensitive to directional motion, so as you were changing the directional motion, you got a nice tuning curve, okay? So it looks something which looks like that as a function of the direction of motion, right? So now here, you don't see anything like that, you know? This neuron you see here, here's the raster and here's the histogram. It responds well to one of these cups from Queen Victoria, but not to another, right? Okay, so it's not a cup neuron, and it does respond to the bear here, but it also responds to the cow. So, okay, we can't think about here about neurons being sort of the grandmother cell. Okay, so one has to think about this from a different perspective, okay, because it doesn't seem to be clearly tuned to a specific category of stimuli, okay, and that's very much related to what you'll hear today. So here's just another example of these neurons in V4 and IT, which you'll hear today. So you look at the response, that's from the time of the image onset. So you see there's a relatively long time until it starts responding, maybe 120 milliseconds. So, you know, okay, it takes a while until the stimulus cascades. So you get first activity in the retina, and then V1, so on and so forth. And since this is sort of far removed from the retina, maybe 5 or 6 steps, it takes quite a while until it starts responding, okay? That's another point. And you see that, okay, it responds to, here's, you see the images, it responds to the, I don't know, to the best to this chair here, but also responds to umbrella. And you see the worst stimulus is, I don't know, the elephant here in the car. So there's no clear tuning here, as I said before. So one has to think of it in a different way, and one has to think about this in terms of a distributed representation of objects. And you'll hear more about this. This is where I stop, because this is exactly where we have to, I want to give time to the students. So just, okay, critical questions, and we will talk about this. If not, I mean,
it's hard to believe it. The question is it consistent in time? The same neuron will still be preferring the same
if you do this,
the umbrella, and I don't know. Because it's hard to, when I look at it, it seems really weird. Okay.
So how
but is it at least consistent?
How reliable is this in the sense that if you come the next day and record from the same neuron, you get the same preference of the neurons? Difficult to answer, because most of the time it's, you know, let's say, when they did these experiments, the technology was not such that you could actually record for many, many days from the same neurons. Maybe not.
There is a group that did that, actually took up electrodes and put it for many, many days, and was extremely stable.
I know that in hippocampus they did.
No, in the
yeah, but I think that, yeah, generally it is robust. I mean,
it did exactly that. They electrodes, kept it many, many days, gave them every day, saw the shapes of the weights were the same, and they found it was very stable.
Okay, so when we're talking about distributed now code, we're thinking about, you know, that you shouldn't look at one cell and see how it's responding to one object versus another, but you should look at the sort of the vector of response you get for one object and another, and see the difference between them. And you'll hear all about this in the coming lecture. So this is where I stop, and okay, the first lecture we'll hear now.
So we already started talking about object recognition, and we'll try to expand on it. So the ability to recognize objects despite changes in size or position, context, also the exact angle, the orientation, its concealment, is thought to be achieved by computations that increase both selectivity for shape selectivity, and transformation tolerance of the visual representations at successive stages of the ventral pathway. In this study, we look specifically on the two latest steps, which are B4 and IT, the inferior temporal cortex, and how they can discriminate between and generalize across different images. So we already saw like some slides for the ventral pathway, but I'll only add, because I want to try to be quick, that it's usually referred to in the simplest way the what, the ventral what pathway as opposed to the dorsal where. So it will be more connected to object recognition. Well, object recognition, we know, requires selectivity for complex feature conjunctions, and not just local features. And they should be invariant to changes in what we said, position, size, context. Well, we think from previous studies that constructing a computational representation that is either higher highly tolerant or highly selective is more trivial, and the challenge is to do both at the same time, simultaneously. Some older papers showed evidence for tuning for more complex stimuli. That's the simplest way, meaning more complex than simple lines. In V4, in V2 and upwards, in V4 and IC. And so they already show that it's selective more to complex objects. And we'll start where Udi actually left off on Sunday, which is not the main study we'll show, but this compares V2 to V1, so we have like the complete spectrum later of V4 and IC. And we already saw these figures, but I want to stress some points again and to remind. So they wanted to see if V1 and V2 respond the same for some images, or where does V2 change its response. So maybe we talked about it a little bit, but I want to show also the method for creating the images. So they started with natural textures, and then using filters with computers, they try to imitate the responses or the tuning of V1 neurons. So they use both linear filters, which correspond to simple V1 neurons, and energy filters, which correspond to complex ones. And starting with white noise, they use a gradient descent mechanism to adjust each time in looking at local features, but not constricting them to the same place they were before. And they try to recreate the statistics of the original image, meaning mostly the spatial frequencies and the orientations, and also the general luminance level and the differences. What they add later to have a really good correlation between the images is they add some correlation between neighboring receptive fields. Okay, and with only these two factors, which we'll expand more for the main study later. They try to compare these images, which are very highly correlated with the original ones, but you can see that the global structure is not exactly the same. So again, Udi says this, but if we look at specific neurons, we see that in V1 there's not much difference. These are single neurons, and this is the average. We can see like a brighter spot here, which is the difference. Then V2, which V2 has a really lower response for these scrambled images as opposed to the original ones. So this is again the average, and this is the difference. So we can see better that there's still some difference in V1, but it's much higher in V2. And they also show it for the specific types or families of images, so that they can show that all of them has the same, show the same thing, or pretty much. And also if they look at population, they see that V1 neurons don't change much. Some of them do respond more for the scrambled or less for the scrambled, but they stay in the average, while V2 has a shift that all of them respond more. And the modulation index, which means the difference divided by the sum of the responses.
Do they also have show responses to the natural images?
It's these, like the
natural, real natural, not scrambled.
yeah, the scrambled is the lighter traces here, and the darker are the natural.
That's the whole point.
There's a differentiate between the natural ones and the artificial ones, having the same statistics.
If you'll be interested more later, we can talk about what we did before with the information, but I want to show the main paper. So, in this V4 in IT paper, we start with the basic methods. The subjects were two male rhesus macaque monkeys, and they recorded using a single microelectrode and serially recording, like putting it in further until each time they could separate one neuron and show him the whole range of stimuli, and then go for the next one. We see here already the receptive fields, which are smaller than before and also really separated between both hemispheres. And IT is more showing in both hemispheres most of the visual field. To try to see how the monkeys could recognize the images or differentiate between them, the responses were added up. Later we'll see how. And discriminability was measured with a linear readout separator using separate vector machine, what's called vector machine. And that's it, just talking a little about the way the stimuli was presented. It was in some random series between 2 and 20 images at each run, each for 200 milliseconds. And the second monkey had some behavioral task, and when he sees a motorcycle.
It's really relatively irrelevant here. So
yeah. So just to say that he didn't make
right?
a difference at the end, but they wanted to show that if you need attention at all to change the responses. So how do you measure discriminability? And so first they collected the spike counts for each neuron responding for each image for many times, and then they put them all together to create some response vector of each neuron, how it responded for this image at this one presentation. Then they put it in the space of all the neurons. Here we see it only in 2D, meaning like two neuron responses. And they plot each of these vectors as one dot. Then each representation of the image, they get another dot. And we see that we get like a cloud of the response. And we note that to separate it with these separating hyperplanes, here just the line, we need like a pretty big distance between the different images clouds, so we can separate it computationally. Yeah.
How do you see the two neurons in the first one?
Here,
No.
it's supposedly these two. So you have just the spike count in this 200 millisecond window, and you plot the spike count. I think it's very high.
How do you see the difference? I mean, how do you see both neuron 1 and neuron 2?
So they're not recorded
Yeah,
simultaneously.
they record each one like serially, each one later, and then they just add up this neuron response and that neuron response for the same image. And
But the same trial in the same image, right? So they record each neuron separately, absolutely, but they don't, and they have, let's say, 10 repetitions of the same trial, the same image, per
For
neuron,
each neuron,
okay?
yeah.
So they look at repetition number 1 in neuron number 1, and in number 2 and number 3, and that's what the vector you see. And it will be different if you look at repetition number 2 and so on and so forth.
yeah, but because okay.
And of
But
course,
we see that it's
somewhat
pretty close.
artificial. The way to do it is to record them all
Yeah.
in parallel, okay? But given that they haven't done this, that's the best they can do.
Okay, so then using these vectors, we try to train the system to discriminate between the different images by creating hyperplane with vector machines, and then we test with the remaining 20% of the responses to see if we get the responses, if we can say if it's this image or another one. So plotting it here along this side of the hyperplane means that we get a correct classification, and on the other side we get the wrong one.
Is that clear to everyone? So that's really the key aspect here in the model. One has to understand that. I mean, everything else is just details. So that's really a crucial thing to understand. So
Just the graph itself.
Okay.
With the axis of the neurons and
Each axis shows one neuron spike count, and then it all becomes in a very high dimension, and you need to learn about linear discrimination, but we won't get too much into it. But the idea is just having some line, knowing which hyperplane. You can do it also with transformations and not just on this simple one. Just to try to separate in the best distance, so in the highest probability you'll get the right answer. You can discriminate. And you do this for each of the image to discriminate between one and no other images. Then you measure it.
So it's just the point is that, okay, to draw it, you can only draw through neurons, but you have to think about, you have a vector of n neurons, so it's in an n-dimensional space, and you have these sort of clouds in n-dimensional space, and you want to separate between these different clouds corresponding to different images. That's the idea. Yeah, go ahead.
Just to make sure, so the classifier gets a vector of the activation of all neurons and
So to see if these regions are more really selective for some natural stimuli and it does not respond just as V1. If V1 doesn't have much change, we did a similar scrambling. They did a similar scrambling to the former article using the same mechanism, only slightly different like emphasis on the stuff. But they want to try to see the responses for specific feature combinations, what they call conjunction sensitivity. And to realize each neuron what it's best tuned for, we have to tailor the stimuli for each neuron, and that we don't want to do. We want to see the whole population, how it can differentiate between them. So we start by analyzing with some 700 parameters of the local filters, like in these sizes, like an eighth of the screen and a quarter and a half and so on. And we try to recreate the spatial frequencies and the orientation in each one, and also the luminance level. So again, starting from white noise, we each time try to recreate these local features again and again, but in different positions. So we assume that the V1 will respond really the same, or really similar. And we get some like features that also resemble the original picture just from having these larger fields or smaller spatial frequencies that also respond to the same phase. So we get some of the main shape, but we can recognize which object it is. Okay, and to see some of the results for this test, trying to compare the ability to differentiate between the natural images and the scrambled ones, meaning if we get the response, if we can say which natural image it was, and if we get the responses for the scrambled, can we still say which scrambled image it was? So this is the hypothesis that uh, that the natural images, that all areas will respond pretty good, will perform good in the task of separating the natural images, like here, that they can still separate them. But in the scrambled images, if we start in V1, say, we can still separate them the same way, but as we go along the ventral pathway, and specifically in V4 and IT, they'll get mixed together and the algorithm won't find a way to discriminate, And now we can look on the results. The black dots are showing for the natural images.
So explain why in the early areas you expect that performance would be high both for the scrambled and the natural.
Because we saw that the responses don't differentiate much, because the local features are still the same, and the correlations between them aren't so are more different, but most of the neurons respond the same, because in the same spot in the receptive field they still have the same orientation and
so I think the point is that if you look at the different scrambled images, go back to the slide before, maybe that would be helpful to make that one. What is the difference between these different natural images and scrambled images? If you're to look locally, there's a great difference between them. So they're not equal in terms of what the local contrast looks like. So that's why you can, at V1, at the V1 level, you can easily differentiate between these images, right? And so it's also true for the natural images, because locally they're very different, okay? As you're moving,
but there's not like an object that you can identify.
Yeah, nothing to do with objects.
That's what I think.
No, but the task is to differentiate between the different scrambled images, right? Okay, and so that's what.
What I think the higher areas do is that they're regular to seeing, they're more used to seeing the natural images, so they're not so used to being able to say what they see here or if it's the same. That's the idea, that they're more practiced on seeing real life stuff.
And they're sensitive to combinations, as I said,
Yeah.
future combinations, and that's why you retain the ability to discriminate between the natural images, okay, but you don't have this for the scrambled images. That's
so why do the neurons in V1 respond the same to the natural and the scrambled? They're also different.
No, like we get pretty much the same in the local specific areas in the luminance, but we saw that before.
Between the natural and each of the scrambled images matching it, right?
Yeah.
So these have the same local statistics. And
Locally
these,
it
just
doesn't seem
the
the
pairs,
It
the
doesn't
pairs.
seem exactly the same, but it should still respond the same. And
Oh,
here we don't
overall.
compare it.
Yeah.
We don't compare it in V1, but the earlier papers did. And it wasn't the same scrambling, but we see that it's a good enough system by the results.
It's actually quite beautiful. I don't have the image here, but they actually have a presentation where they show an image, and an image which has the same local statistics. If you keep the same at the foveas, at the area where you're fixating, you cannot tell the difference between the two. Maybe I'll bring this to show you this to you. So actually, we are, they're called sort of metamers, that you really can't tell the difference between this image and that, and you're saying, that's impossible. But I'll try to show you an example of that. Indeed the case. Okay, go on.
So going through the results, we'll see that no matter what size of population of neurons we take, until all of those that they recorded from, we get higher performance, higher discrimination performance for the natural images and the scrambled ones, both in V4 and IT. But the difference is much, much higher in IT, meaning the performance for the scrambled images for the entire population of neurons is like 33% versus 74% for the natural in the IT, and closer for the V4. We can see them summed up here for the entire 140 neurons population. And if we try to go further and, according to the hypothesis, try to equate the performance for both V4 and IT, mostly because we don't get the entire population of these regions, so we can say that the absolute performance. But if we equate them, then we still see a really large gap. Like the natural performance remains the same, but the scrambled one goes much lower from V4 to IT. Okay, this corresponds to a little less neurons in V4, 120.
How many or around how many images, different images?
It was 50 images,
50 images.
50 image, and then 50 scrambled versions.
No, I mean
in
how
this
many
part.
classes that you need to
Yeah.
discriminate?
So each
Start from
discriminating each
Pairs-
one from
two
the
pairs
other.
level,
Two
basically.
pairs, you had two images from the bank of 50 images, so there's no...
All right. 15.
Yeah, yeah, but there's much more pairs that you can compare.
No,
You
of
do the
course.
average, right?
Of course, of
Yeah.
course.
One thing that maybe you should stress is, okay, why when you increase the number of neurons you get better? That's important to understand. Can you give an intuition for that?
You'll get a wider range of responses. So some neurons will respond more different, so you can give them higher weight in the decision, and those that don't have too much difference won't change.
Right, so you want to discriminate between these two clouds, right? Image 1 and image 2. You add another dimension.
Yeah, you add more
another
dimension.
dimension, you can separate them on the third dimension. If you go, so if you're following the logic, maybe if you show the first slide. This is important, you know. Actually, it's not really critical that we go over all the paper, but it is critical that we understand what we're talking about. Okay, so one has to understand why, as you increase the number of neurons, you get a possibility of differentiation. Every time you add another neuron, you have another dimension, right? So you're going from, if you have two neurons, you have two dimensions. You add a third one, you have a third dimension to separate the cloud, and so on and so forth. So you expect this to rise, of course, okay? Because you have more degrees of freedom to sort of pick up how to separate them. Okay, sorry.
You can sit like here or
No, I prefer standing up. But okay, go.
So just to say one line conclusion from this part, we see that both of these regions are more selective or better selective for the natural images, but IT is even more, as we said, scrambling sensitive. So if we show something that doesn't make sense in the conjunction of the features, it will do a much worse job in discriminating between them. And we move forward to the second part, which is tolerance.
One question?
Yeah.
B is V4 is better than IT, right? In the black.
Yeah,
And then
with the same size
Yeah,
of population.
now what's the difference between B and C?
So D tries to equate the performance for both of them. So it uses, this is just the same picture, but trying to show that these
How
would
many
be,
neurons you need?
yeah, how many
One
neurons
picture.
you need to have the same performance,
When they have the same
just
number
from
of
the
neurons?
hypothesis.
When they have the same number of neurons, V4 is better than IT, right?
Yeah.
Why is that? Do you have any institution for that?
And they have different number of overall neurons in both regions.
So they're using the same number for the computation here. Good point. I don't think we have a good answer to this, except that they're focusing that V4 does better also when you compare to the scrambled images. So okay.
Yeah, that's
So remember that the scrambled images, V1 would do great, right? Okay. So it's not surprising. It would do great. It would do great both for the scrambled images and the original images. Okay. So what they're trying to emphasize is this difference.
Yeah, that is, yeah.
But I'm trying to say that you
That's
can
right,
compare the same number because
Right.
they don't respond to the same thing in both regions. If they have the overall number the same or in the same region where we show the image, you can talk more about it. But
Okay, now we can defer the sort of the break until after this talk, which I prefer to be the case, but then you have to be patient. Okay. Yeah.
Yeah, we will-
trying
Do
to
we have
do.
a quick or no?
No, go ahead. I think it's better to sort of follow up on that.
Okay. Except the selectivity, tolerance is also very important for object recognition. So how do you say? Okay, we know this is the president of United States, Trump, right? This is Trump in the middle, Trump on the left side, Trump on the right side, big Trump, small Trump, Trump with different background. We know it's Trump, right? So our visual system have this kind of ability to recognize the identity preserving transformation. So how our brain do that, and what's the information flow in our visual pathway. So let's start the tolerant part. So before we're doing research, so let's set up some criteria first. So if we see one image for several times, then we can distinguish other transformation. We call this good generalization. And if we cannot, then we call it bad generalization. And since the lower visual pathway visual states are responsible for feature extraction, and higher visual states are responsible for feature integration. So we will so they assume that the generalizability will increase along the visual pathway. So in order to perform experiments, so they need to generate data first. So they generate this identity preserving image by scaling, shifting, and changing background. Before using this image, they need to show that after this kind of transformation, the neuron could still differentiate this image. For example, they train in big image and test on the big image, and they found that the performance is still very good, and so as other groups. So they will think that image after this kind of transformation could still be differentiated by the neuron. Yeah. Okay.
But is this the individual neuron you're talking here?
No.
You said performance. What do you mean by performance? Because it's not the individual neuron. Right?
Yeah. This is a group of population data, as what we see before. Yeah.
Exactly.
This is the population data. Okay.
Is that clear to everyone?
Is that too far?
Please ask questions. It's something, I'm asking questions because I'm sort of preempting you, but please ask questions. If you don't, I will not ask any more questions.
Population data?
So just as Ilan showed before. So population data is that use a lot of neuron to do the differentiation. So a lot of dimension.
So you remain with this slide, just to make that clear, okay? You trained with this image here, and you get that sort of responses for that given image, and you test how different it is from another image. Now, I guess what they do is instead of taking this image, now they move it to a different position, they get another cloud, okay? But the cloud is very close to this one, so you can still discriminate between this and that. So that's how you measure performance, okay?
And similar to what they did for sensitivity. So this black line is trained on reference image and the test on reference image. So the performance of this black line are considered as perfect performance. And we can see there is a dashed line here, right? The dashed line is trained by the switch label. Yes, in response for the question you asked before. So this dashed line is considered as background noise, right? So and the black line is for the generalizability. So it's trained by reference image and test on the transformed image. So as you can see from this graph, so the performance of IT is better than the performance of V4. And the more neuron you use, that means the more data you get, right? So this difference becomes larger and larger. And so as to the transformation, the stronger you do the transformation, the larger the difference about generalizability. You see here, this is shift a little bit, shifted a lot, scale a little bit, scaled a lot. So you see the difference become larger, right? the difference become larger. So yes, so it,
Any intuition for why would that be the case? Trivial intuition, okay, related to the first slide that we've had about, you know, IT neurons versus V4 neurons.
If you don't think about it, then you see it.
yeah, we will give indication after.
Go ahead, sorry.
Okay. So
We're just asking them to. No, but go ahead, I'm sorry.
Okay.
You're right.
Okay, so now it seems that result is compatible with with their hypothesis. Yes, but one may argue that so this is really not the case. We recognize image. So for example, when I meet you for the first time, so I will try to recognize your face, right? So the distance between us may change, and you have them move. The input to my brain is not just one image, but a bunch of these kinds of identity preserving transformation. So now let's divide the tolerance in two different levels. So one is generalized level. So as we discussed before, so it's seeing one image, only one image for several times, then I can recognize other transformations. This level is high standard and it's hard. And then another level is relatively easy and more natural. So it's like I recognize I see the reference image and see some transformed image and test on other transformed image. So that's okay. Yeah. The same as what I said before, train as reference image and some transformed image, and test on other transformed image. So you can see, as you can see here, so it's the same result. IT also perform better than before. So now we can conclude that no matter for generalizability or the linear separability. So okay, sorry, I forgot one thing. They call this linear separability. Okay, so no matter for generalizability or linear separability, so IT have a higher tolerance than before, right? Okay, so all the data we showed before are population basis. What about single neuron? So let's take a look at it. So this is single neuron data. So ROC here is represent the ability to differentiate the two images, and the higher the value, the stronger this neuron could differentiate two images, and they divide the neuron into several beams based on the ROC value. You can see there a lot of beams. So and the y-axis is the performance of the ability of the neuron to recognize the scrambled image based on the reference image. That's the part Ilan saw before. And as you can see over here, so right, compare the first bin of V4 to first bin of IT. You see that the performance of V4 is higher than IT, right? This is single neuron level. So and the second one higher than the second one. The third one higher than the third one. So so on and so forth. So now we can conclude that in single neuron level, V4 perform better than IT, right?
That's for the scrambled images, right?
Yeah, this is for scrambled image.
What about the natural?
Yeah.
No, the red is scrambled and the gray is natural.
Yeah, this red is.
So for the
Red is
yeah, there's still a difference, but not that.
Yeah, not that much.
Not that much, right?
Yeah. Okay.
Anyway.
Okay.
But here it's single neuron, right?
Yeah, this is single neuron.
Not a population called single neurons. Okay.
Yeah. This is single neuron. Okay. Okay, and this is compatible with the population based result Ilan saw before. Yeah. Okay.
So I'm confused because in the previous slide, the IT neurons perform better.
No. This is tolerance.
Yeah, this is again.
This is tolerance.
What?
Tolerance. So this is because
changes in position, tolerance to changes in position or in scale. That's what.
Yeah, and this is the result of scrambling. So this is the part Ilan saw before. Okay.
Explain again what's the x-axis, what's the
Yes.
y-axis?
X-axis is the ROC. ROC is the ability of one single neuron to differentiate the two image.
Okay.
Two image. Okay. The higher the value, the stronger the differentiation. Okay. And the y-axis,
just to give an idea, since it's two images, the ROC is limited between 0.5, there's no information, and 1 is maximum information, right? Okay? And the ROC is somewhere in between, and you see that it's generally, I mean, I think that the point you want to make is that this comparison, no? That this here, okay?
Yeah. The
this
most of
and this, okay? So this is for scrambled images, and this is for natural images, right?
Yeah.
Okay. So
Yeah.
How do you define the ROC? I mean, how do you determine?
remember that we talked about these two distributions? That you have a distribution for the one stimulus and a distribution. This is stimulus 1 and stimulus 2. ROC is the difference between them, right? So that's the firing rate you get for one and for the other. The less of an overlap you have, the better discriminability. Okay? So that's what you see. So maximum ROC is 1. Okay, and certainly that these neurons have information above 0.5, because 0.5 is just chance level.
And the performance is a behavior, or is of the I mean, is
So-
it neuronal thing, or?
Oh, okay. So you mean the y-axis, right?
Yeah, the y-axis.
Yeah, the y-axis is so y-axis is like for each single neuron. I see it as a classifier. So we will see one single neuron as one classifier, and we train this single neuron. Use the reference data, and test it using the scramble image. And we want to see that if this neuron could recognize the scramble image.
So I just to make sure I understand. The
Okay.
neurons that you use in order to define the ROC are different than the neuron that you use for determining the performance?
No, the same neuron.
So the correlates, you see the ones having higher ROC are also the ones having better performance, right?
Yeah, these two.
No surprise there, that's what you expect. Okay?
Okay. And the same with the tolerance part. So we see that this axis is RC, and this axis is the performance of linear separability. So you see here, the first ping of IT is higher than the first ping of V4. The second ping is higher than the second ping of V4. So on and so forth. So in this part, we can also conclude that in single neuron level, IT perform better than V4, right? So this is compatible with the population result we saw before. So but what's the underlying mechanism for this single neuron property? So they also try to connect the single neuron property with the receptor field. So for here is the position in sensitivity. The larger the receptor field size, the larger the position in sensitivity. So as you can see for this graph, as receptor field size increase, the neuron will be more sensitive to scrambling, and the less selectivity, right? Okay. And for taurine part, although we couldn't see the relationship between receptor field size and linear separability directly, but we can see that after they match the receptor field size, so they use the IT neuron and the V4 neuron, they match the receptor field size. They just select some neuron and do the population training again. So you can see that the difference between this linear separability becomes smaller. So they conclude that the receptor field size also contribute to the linear separability.
Okay, maybe I think that let's try to sum up and get to
That's sum up. Okay, let's back to the two hypotheses they showed before. So low level visual states have a small receptor field, and the higher visual states have a large receptor fields. So if you give noise block by block while keeping the local feature. The larger the receptor field, the more so this noise will distort the feature conjunction, and the large the receptor field, the stronger the distortion. So low visual states with small receptor field will have a higher selectivity, right? So and for the selectivity, so higher visual states have a large receptor field. So they have higher chance to keep the conjunction of the feature conjunction inside the same receptor field after the shifting or scaling. So for example, here is the case. You can see the nose and the mouth inside this small receptor field, but after shifting, so it moved to another small receptor field, but it's still on the large. It's still on the large receptor field. So we can see that large receptive field is more tolerant for shifting and this kind of thing. Yep.
Okay. You want to raise just a couple of points for discussion, just for them to
So
think
just
about
to summarize,
Yeah, just to summarize.
We think it's a very nice paper and a good topic to try to say what the hell these higher regions do exactly, how is the information represented, and what processing happens. But we do have some criticism maybe, or stuff that some other people or them can do further, is for one, unifying the account for all of the regions, at least all of the cortical regions, and not just two at each time, which might be hard. Also, the algorithms for the discrimination, they're computer algorithms. They can reflect, and they did try some other ones and showed the same result, but it still might not be exactly how the brain does it, and some presuming. And
what part you think is artificial in terms of how the brain does it? Which part?
just saying that discrimination happens by this linear discriminator with the SPM and specific kernel. And another thing is how are these functions formed in doing life? Is it by motion perception that we see some image and then it moves like continuously to another place and we know it's the same one? Or is it by experience that we see more natural stimuli? And they say that if you train the monkeys to see these scrambled images, they might be able to discriminate them the same as they did the natural ones, or better. That's what they use. That's for you.
Any other comments before we break? I have one major comment, and I think that one major flaw in the paper is that they have not recording the neurons simultaneously. So they're making an assumption, which is a very simplified assumption. Remember, they're taking the firing rate of the first neuron in the first trial presentation and showing it together with the firing rate of the second neuron in the first presentation, so on and so forth. So this is a completely artificial representation, and it's also problematic because the actual firing rates of the neurons may be affecting one another.
Yeah,
so
like correlated
so
in some way.
Yeah, correlated. So what we're discussing, noise correlation, right? And so in that response, they may be changing together, and that's completely ignored here in all their analysis. So that's something that has been, can be improved with the capability of recording multiple neurons, which has evolved tremendously. This is like from 9 years ago, something like that. So there's been this is something that one can answer more straightforward than nowadays. Okay, we'll take a break, but it'll be short because we want to give time for the so let's make it at 5:10. Let's make it like 7-minute break just so you can go to and then we start so we have time to I mean, we didn't talk about that, but you clearly understood what we were talking about, what the paper was about. You made the point very well. האיש לכם הפוינטר, אתה משתמש בזה שאתה יכול לעבר אותו, שאתה יכול לזוז אם אתה אוהב את זה. כן, כן, כן. הצלחתם להבין לגמרי בכנות, נו, מה שאתה תגיד. ראשית, אתה מרגיש כאילו שאני לא אתכנס,
אצלנו?
כן.
זה לא היה עם
זה עזר שעשיתי את זה עכשיו טוב.
זה סתם כאילו רעבים.
האם זה סתם כאילו הוריך, אז ברור שזה לא עזר.
לא.
השאלה זה עזר להבנה. האם, כאילו, הנקודה היא...
טוב, אני הבנתי כזה חלק מהדברים קשורים למה שאתה יודע, אז כזה הבנתי יותר.
כן, כן, לא, אז אני לא אחר, רק כדי קודם פעם.
יש לנו שנראה על דיין, אתה רוצה, כאילו...
לא, אז אני שואל שאלה כזה רק, אבל אם זה מאוד מפריע, אני יכול לא, זה לא...
לא, האמת שאני...
כאילו, אני לא
מקווה שזה יהיה, כאילו...
לא חשוב לי שתעבירו את כל החומר, באמת. מה שחשוב יותר זה שכאילו תהיה הבנה יסודית של השיטות ושל התוצאות הכי ראשוניות. תציגו 3 סליידים במקום 5, זה ממש לא מפריע לי, באמת שאני לא חושב שזה חשוב. באמת שזה חשוב, ולכן הדיון...
אצלנו יחסית יותר קל, כאילו...
כן, אבל זה חלק מהעבודה.
גם, אבל גם כאילו המועצה יותר...
פיזיולוגי.
יותר מסובך נראה לי מה... כאילו
לא בטוח, אני לא יודע.
הניתוח שהם עשו שם, כאילו יותר... כאילו, אתה יודע, שינו תמונות, שינו זה, כאילו, גם... חלק זה... קיבלת את זה?
לא, רגע.
פשוט עדיף לפני שפותחים את המצגת לעשות את זה. כאילו... מה עשיתי שם?
תראי, רגע לא תנפה?
להיות שונות לאיך...
ללמידה. כן, דיברתי על ה-decorrelating.
decorrelating זה כאילו משהו כמו whitening כזה, לעשות לדעת, כאילו...
אתה אומר כן, אתה אומר ככה. נוירונים שונים, נגיד הם מגיבים לאותו כיוון תנועה, אתה עושה פול שלהם ביחד. הנקודה היא אבל שפעם מגיבים יותר חזק, פעם מגיבים יותר חלש, והאם הנויז הזה קורלנטי בין כולם, אבל ביחד, זה כמובן מקלקל לך את הביצוע. אז אם אתה רוצה לעשות, אם אתה רוצה לעשות נויז decorrelation, כזה אתה משפר את הביצוע. זה בשתי מילים.
ויש כאילו סיבות ל...
לא, אז רציתי להעלות את העניין של, אוקיי, זה גישה אחת, שלא חוקרים, בדרך כלל מתייחסים לשינוי של ה-weight, וזה חמונה, הצגתי את זה, שזה אוקיי, תראו, גם בנושא הזה של כאילו ה-decorrelation הוא קרוב לליבי, שלא התייחסו אליו, אפשר לבדוק את זה, כמובן, לא עשו את הניסיון, אבל מה שאתה רוצה לראות, אתה מודד את ה-noise correlation, לפני הלימוד ואחרי, תשווה.
אבל זה לא צריך מידע, כאילו...
ממש
כלל למידה שינסה לממש משהו כזה.
אוקיי, אתה יכול להגיד על זה, אולי אני לא מבין, הם מגיבים לאותו כיוון?
זה B1 קורלציה, אבל
I think it should be discussed בדיבור על ההבדל, אבל זה אני חושב, כאילו...
מה המנגנונים הביולוגיים שיאפשרו לך לעשות?
כאילו, שלב אחד לפני, כאילו...
אתה אומר, אוקיי, אתה יכול לחשב, לא הבנתי על מה הבעיה.
לא, אולי לא הבנתי לגמרי מה, כאילו, התחלת להגיד משהו על זה.
אמרתי שראשית, מדיקורליישן מקבל אינפורמציה יותר מהר. עכשיו, איך אפשר לעשות? יכול להיות שאתה לא יכול לעשות. מה אתה רוצה? ממה נובע הנוי? נובע מזה שזה common input. השני ומקבלים את אותו input. common input עכשיו פעם אחת יותר חזק, פעם יותר חלש. אתה לא יכול עכשיו לעשות decorrelating שלו. לכן יכול להיות שזה לא משהו כאילו, איך אתה, האם ביולוגית ניתן לעשות
אולי שלב אחד שלב הבא
כן, יש כל מיני שהיא קונספטואלית כי לא חושבים על זה, בעיקר חושבים על Okay, take a seat, folks, please. We want to give a chance to the second group of students to please sit down. Then we continue. Okay.
Okay, so we are going to present today the article Matching Categorial Object Representation in Serial Temporal Cortex of Man and Monkey. I wanted to give a quick background about it, but apparently you understood it. So just to make sure that everybody knows it, I will do it quickly. The IT is an higher level cortex in the ventral pathway of the visual system, which okay, you have already seen that, so I'm just going to move away, but pretty much the IT is an higher level region in the ventral pathway, and the ventral pathway is about extracting the semantics of the visual stimuli. So what the ID is believed to do is to extract the semantics of the visual stimuli, and we're going to see a bit more about that.
Semantics, I mean, recognize the image.
Yeah, recognize the image.
Maybe I can ask you, like in humans, is it also called IT or is it something?
Yeah, it's also called IT.
In humans, yeah.
Okay.
Okay, so this article had a major 2 points to it. The first one was to understand the role of the IT better, and the second one is to try to compare the activity of the IT in both humans and monkeys. Now, this is a very not trivial comparison, as those are different species. And not only those are different species, the research about the monkeys was done previously to the one that they did here. So they already had all the data of the monkeys using electrophysiology. And this is not possible in humans. So in humans, they did fMRI study. And they also tried to compare between fMRI and electrophysiology, which is also not very trivial. Okay, so let's see what they did. They had 2 monkeys and 4 humans, and about 92 images of all kinds of different objects, including humans, faces, body parts, inanimate objects that you can see in nature, such as fruits and vegetables, and inanimate objects such as traffic lights and chairs and stuff that human made. The task was just to look on just a simple fixation task, and the images just flash in your background while you're doing the fixating task, and they record the activity in the IT in monkeys using single cell recording, and in humans using fMRI. Okay, so why is this another problem? First of all, those are different species, which is really not easy to compare between. When you take two different species and try to compare what they're doing, so first of all, they're not doing the same task. The humans, you can just ask them to fixate and hope they will do it and see the image. Monkeys, you train them for a very long time in order to achieve that, and it's not clear that what we are doing is actually what the human does. Second of all, both monkeys and humans have very different background and history. Humans grow in an environment that they know what chair is and what traffic light is and what a tiger is. Monkey doesn't necessarily seen any of those stuff before. Even not the natural one, since it did not grow in nature, does not necessarily know what a tiger looks like, and let alone a traffic light or a chair or something like that. And the last thing is the brain structure of humans and monkeys are very different. The human brain, as you can see, is much bigger, and also the IT of the human is much bigger. There is some homology between the two, but this is really not a trivial comparison, and you can not really just go on and do it. The second
What are you suggesting? What are you suggesting?
That doesn't make quite sense.
Okay, the second problem in the comparison is that the usage of different methods. First of all, the temporal resolution of both methods are completely different. The single cell recording stuff in the order of milliseconds, just recording the voltage that is come from the cell, while the fMRI is scanning the brain once every 2 or 3 seconds, and temporal resolutions are completely off scale. And the spatial resolution is also very different. In single cell, you're in the order of micrometers in just recording the cell, while in fMRI, you're looking at voxels of about 5 to 10 cubic millimeter wide that contain over 100,000 of neurons, and sometimes even millions of neurons each voxel, while the single cell is, of course, a single cell. And the last point is that the signal that both of these methods are measuring are extremely different. In the cell recording, you're measuring the direct voltage, and in the fMRI, you're only recording some sort of correlation to the activity by just taking the volt signal, that is the amount of oxygen in the blood in the area of the neurons, and hoping that this will respond somehow to those activities. Note that those signals cannot be compared directly. They do not correspond in any way, and this is issues that need to be overcome, and Yoav is going to tell you why.
So now we'll show you how we can still compare the two data, and even publish a paper in Neuron about it. So first thing, let's just guide you through the analysis they did. So first thing, we flashed the image. We recorded both in humans and in monkeys. In monkeys, we had a single cell response. In humans, we had the voxels of the fMRI signal. Now, the first thing that we want to do, both these measurements measure over time, and we want to get just a single average value. So we average over a time window. And then, so we get for every neuron, for example, for the single cell, or for every voxel. Notice that this whole procedure can be done for any method in general, and even for a computer simulation. So we'll stress it again later, but it's sort of independent of the measurement of the measuring device. So okay, and even like for the different measurements, when we measure over time, we will need different time windows to measure, and still we'll make sense out of it. So once we measure we're just limitation, I'm going to call each neuron or each voxel or each unit that we measure, I'll just call it cell. And once we average over time, we can construct this sort of matrix that we have the different stimuli that we give and the different cell response, where the value corresponds to the mean or average firing rate or stimulus. And now this matrix, we can first of all look at it in two ways. Once we can look at the vector of the stimulus, like what the response that each stimulus gives. And the second thing, we can look at different cell response. So before we go into the main analysis, there's an issue that it's possible that some cells will fire much more than others because they're more sensitive or just have a different baseline. And this will just give stay on, and the real information that we're looking for is the different response for the different stimuli. So we'll need to compensate for this baseline, for this bias. So the first thing we're going to do is each cell will want to normalize the values. So we do that, and then the next thing, we're going to take now the column vectors of the matrix we had of the different stimuli and the normalized response, and what we're going to do is to find the Pearson correlation, which we denote by R, between every two stimuli. Okay, so what does this mean? We can take, for example, every two stimuli. Here the axis responds to activation values, the main activation that we computed, and each dot represents a different cell. So we can plot them and then estimate the correlation, which basically means how much the two stimuli response is linearly dependent. So if there is no relation between the two by the response pattern, it will look Gaussian and we'll get that R is equal to 0. If they're similar, the two response patterns are very similar, such as you can see here, it's also a nice way to visualize the similarity of the two patterns. If it's similar, we'll get R closer to 1, and if it's still a straight line but it's downward, which means that that they have an opposite activation pattern, then R will be closer to -1.
Can you differentiate between cells and from the fMRI?
So, but right now, all of this we can do here any different method, but this is just for one method. This is just done for, let's say, now go with a single cell recording. So now it's all data from the single cell recording.
But the same, you can do the same for the MRI.
Yeah, we can do the same for the
the
the procedure is the same. So this procedure is exactly the same for all of them, and that's one of the beauties of it. Okay, so once R basically means one is similar and -1 is not similar, but in the paper and another way to do it, we just define the dissimilarity distance now, which is just basically 1 minus R, and this ranges between 0 and 2. 2 is opposite activity, 0 is similar activity, and 1 is sort of independent activity. So when we take two stimuli and we compute the dissimilarity value between them, basically means how much the response pattern are going to be dissimilar, less similar. And we do that for all the different stimuli, the 92 stimuli, all the combinations of them. And we can construct this huge matrix, which we call the RDM, the representational dissimilarity matrix. Notice that red, the warmer the color, the more dissimilar the two stimuli are. And notice some more issues about it. Since the correlation is symmetric, this whole matrix is also symmetric across the diagonal. So basically, it's enough to just look at the upper triangle. And it's also worth noting that the whole procedure, the researchers also tried different normalization technique and a bit different correlation methods, and the results are consistent. So it's a pretty robust method to use. Okay, so now let's take a look at this.
I have a question.
Okay.
You also tried
If
What
they
do you
did,
mean
they
by
did not
not?
write it. If they did try, they did not write it in that.
The non-linear, no. Yeah, and actually another important thing about the correlation is that it also accounts for different measurement artifacts. So, for example, if one stimuli the human was more focused or something, and then all the response is larger, then it will still, like, the vector of the correspondence will just be longer or something, but the correlation compensates for that. So it will still give the same values. Okay, now let's look at larger, appreciate this, the RDA matrix for a second. First of all, the stimuli was arranged by sort of naive categorization. So you can see that we have animate objects, inanimate objects, and between them we have natural and artificial. We have human, not human, and then even a smaller separation of body and face, and again body and face for the not human. And between these clusters, the arrangement was done sort of to maximize what we'll call clusters, which are basically blocks in about the same color. So the first of all, probably the most striking thing that you can see is that this matrix is broken into like 4 quarters, like red, blue, red, and blue again. And just to understand what this means, so we said that red is for every red point, the two stimulus are very dissimilar, the response pattern. Basically, it means that anything that the inanimate response pattern and the animate response pattern were very dissimilar, while for animate, two objects that were animate, the response pattern was much more similar. Notice that this is for the human using the voxels. Soon we'll see it also for the monkey. And just some other things we can notice is, besides these 4 major clusters or categorization, because it also implies that there is some category of animate and inanimate, you can also see like this very obvious square, which corresponds to a great similarity between human faces, human to human faces. You can also see this square here, which corresponds to similarity between animal faces. And even there is a square here, which means that both human faces and animal faces were still quite similar. So, and since these squares are like inside the big animate, sort of give a hint about possibility of subclustering, of subcategorization, or something of a hierarchical structure that we have in there. And as I said before, this from here we just see the correlation between the activity patterns. It has no memory of the specific measurement methods that we used, and to prove that we can look at the monkey RDM that was computed using the single cell recording, and it's strikingly similar. It's just pretty much the same categorization. From first sight it looks completely the same.
Are they sorted the same way?
Okay, so yeah, the monkey idea is sorted exactly the same way as the human. So yeah, like everything is sorted the same way. This could probably, if they wanted to maximize the clusters, they could shift it a bit, but just then it would be a bit cheating if I just change it.
And another question, so did they use the same object animated and non-animated to show that it's the animation, or?
Animated, I mean not it animates objects, alive objects. It's still images, it's not animation.
Inanimate means animals and
Animal,
humans,
yeah.
that in inanimate
Yeah,
chairs
yeah,
and
yeah.
tables, not animation.
So each single point in the matrix, is it a voxel? Is it what is it?
Okay, so each single point is a correlation between, which also makes an important issue, that when we took the data, here it's independent of the number of samples that we had. We could construct exactly the resolution of this matrix depends on just on the number of stimuli. You can't see here how many neurons were sampled or how many voxels. It's true that if the more we sample, the more true these values will give us intuition about the real world. And actually, in the paper, they tried taking just different number of voxels to see if the results are going to be consistent. And
but they're both the same number of.
Yes,
general
both the same number of.
Around 500 or so voxels and neurons. Right?
Yeah, they used about 600 neurons as samples.
And about 1,000
Okay, the same order of magnitude.
Yeah.
And just to,
Did they sort and then put it in the matrix, or did they sort by the clustering that they found that these two things have the same dissimilarity, like they're similar?
yeah. So in the paper there are different ways to cluster and different ways to sort, and they tried different ones to say that it's consistent. But here, if I remember correctly, it's like they first have sorted the stimulus by the major intuitive categories, and within the categories they maximize the clusters. Yeah.
So if I do just using computer vision, do you think I can get the same result?
So that's actually a part we're not can ask later, but they did it in the paper. They didn't show the matrix from computer simulation. One thing is we don't have a good model of the IT yet, so we can do it, but they did try to see if this can be accounted for low-level features that the computer can experience, and they didn't manage. Okay, so let's go on. And so just to summarize what we see here, the same categorization, the same hierarchical structure, and we could one thing that I'm not sure if you can see here, but there is some difference in the faces. The monkey here is really the same color, while at the human there is some variance, which basically means that raises the possibility that the monkey can't identify between human faces while humans can, and also maybe the monkey as here it's more similar it's less similar that's not really the same. It's both similar for the animals, but there is another figure showing later. And so this now is the main. That's like the new data that we're going to use now. We stripped it off all the artifacts of the measurement of the method, and from this we can do further analysis and see things that are hard to visualize just by comparison with the eye. And just before we go into this further analysis, some comments about this. I just showed you all of the procedures that they did. There was no hidden smoothing or assuming priors that happened that they many times use when they want to show clusters. That's like they smooth everything out. Also, the correlations could be compared between the two methods and the species now. Can just even a computer simulation or anything, as we said before. And there is no need for a straight mapping between each neuron and each voxel. So it's independent of the representation in the brain itself. So it's like more of an abstract level. It's somewhere in between the cognitive level at the abstract presentations and the real activity pattern. And now we're going to show you how we can take this similarity matrix and do further analysis.
A little bit short of time, so I'll try to do it quickly. Okay, so as you have showed you, there was the RDA matrix, but it was not very easy to see what's going on in there. It was just big dots, and it wasn't very clear. So what they're trying to do here is to show the images on a 2D dimension, where a distance on this dimension corresponds to the amount of dissimilarity or similarity in the two images. If two images are closer, that means that the IT is responding pretty much the same for them, and if they're far apart, it means that the similarity between them is quite big. The method they used to do it is not that trivial. They did something that's called multidimensional scaling, which is taking all the points in a very high dimension, actually the dimension of the data, and using distances there, and then projecting it into the 2D space, which can cause a bit of some artifacts, but the general idea stays pretty much the same. So we can see here on the here in the circle here, the blue dots and the blue dots and the teal dots are natural objects or inanimate objects actually, and the red and the pink dots are the animate objects. And we can see that both in the monkey and in the human, there is a strict border between them. All the animates going to the left side and all the inanimate going to the right side, which really suggests that the IT really differentiates between those two main categories. And even we can see within category that there is even a better categorization, even a simpler categorization between, let's say, body and faces, that all the body parts and stuff like that, or just bodies, went to the upside of the animate, and all the faces went to the downside of the animate. Just from viewing this image, we can see that the IT does not do anything that's related directly to color or simple shape, because if you look on an adjacent images here, you can't see any resemblance in, maybe in the humans, but you can't see any resemblance in color or shape. So the IT does not compute as V1 just the simple shapes and stuff. It computes actually some sort of meaning. Okay, so they took the two circles they did before, and now they want to, for the first time, to try to do something that is a cross-species comparison, because before that every species was we analyzed every species differently, and we just got a simple one for the human, a simple one for the monkey, and we did not correlate them or compare them in any way. So what they did here, they just took the same two circles as before and drew fibers between them, that every fiber just corresponds to the same stimuli in both human and monkey. And as you can see, most of the fibers, or at least they claim that most of the fibers are quite straight, which suggests that the activity of the IT is really some kind of similar between the monkey and the human. There is also the point here about the thickness of the fibers. The thickness here is done by correlation of the two activity patterns. If the line is thick, that means that the correlation is very, very low, and this is not good. And if the line is thin, the correlation is high, and this is very good. And they also make a point here that most of the lines, and especially most of the straight lines, are very, very thin, which really suggests some kind of correlation between both items. So this was very pretty, but it's not actually correlation. So let's take a graph look.
Correlation of what? Correlation of what?
You have just take the two lines in the RGM matrix and correlate them. The correlation of patterns between the two.
Same pattern in a human and in a monkey.
All lines?
To us, yeah.
For every two stimuli, you take the columns from the RDM matrices and correlate them. So it's basically the correlation between the relative representation in the space.
Okay. So what they did here is they wanted to show that there actually exists a correlation in a more graphical way. In the x-axis here, we see the amount of dissimilarity in the monkey IT, and in the y-axis we see the amount of dissimilarity in the human IT, and every dot here is a pair of two stimuli, and we can see how much dissimilarities are in the monkey and how much dissimilarities are in the human. In the gray dots in both graphs, you just see all the stimuli, just all the pairwise stimuli, which is fairly you can see the correlation just by looking at it, but you can also see that it's a very high correlation and a very significant one. And furthermore, they also showed that not only all the stimuli are correlate to one another, but even if you go to the subcategories, you still get some sort of correlation. If you just compare, let's say, the animates, within the animates, just any two pairs of animates objects, as you can see in the pink one here, you still see a very good correlation, which suggests that both the monkey and the humans are doing it quite the same. And even if you go into a deeper subcategory, let's say humans from the animate, so you can see that even just pictures of humans are still very, very correlative. This is, of course, not trivial and very surprising to find, since there is...
This is face or body, right? Just
Yeah,
to make the point, okay? So, to tell the difference between face and body...
Yeah, they did not take it even further to do between face and
individual
bodies.
faces. I mean, the next step for is to see can you actually differentiate between individual faces, and we'll show that.
Yeah.
Same correlation as we were talking about before, between two columns, or is it
You now, yeah, it's different correlation. You compare from the different matrices. You take one matrix and the other and correlate them. Okay, and however, not everything is correlated, and not everything is very nice, which is, you can see here. Here, they try to, in the green dots, they try to, they put all the human faces coupled, and in the teal, I think, teal points, you put all the animal faces, and you can see that there are two major clusters here that do not correlate in any way. However, this could maybe be explained by the fact that humans tend to differentiate human faces more, and monkeys tend to differentiate monkey faces more, since the IT got some responsibility in recognizing people, recognizing things of your species. So humans can differentiate better when they see other humans, and monkeys are obviously better in other monkeys than humans are.
Then the green dots should have been higher on the y-axis, right? Because the humans...
They are, if you take the linear of the correlation, you see that most of the green points are above it. Both humans and monkeys differentiate humans not that good, but humans do it.
Right.
Yeah. Okay, so to have some control on the results, they try to do the following. They try to just take another location in the brain, here in the V1, and do the same method to it. You just see that we are not getting the same we are not getting the same response all over the brain. And as you can see, when they did it for V1, it looks like completely noise compared to the IT, which suggests that they did not work in the same idea. Taking here the V1 got even some more information into it, since we already know that the V1 uses simple features in order to do its differentiation. So as you can see, since the V1 here does not work the same as the human IT, it shows that not only the IT does not work, it shows that the IT does not use that simple. Okay, and I'm going to do it much more faster now. So.
No, don't be fast. Just one more slide and let's finish.
Yeah,
you don't have to cover everything.
We have one more slide.
Okay.
Yeah.
So, okay, so just to see what we just witnessed here in the IT versus V1 only in graph form. So what they did here is just to take the same graph as before, but do it in with correlation. All the green points are, again, we got in the x-axis the dissimilarity in the V1, and in the y-axis the dissimilarity in the IT. And the green points are all the pairs of animates with animates. The teal are inanimates with inanimates, and the red ones are the pairs that are cross animate and inanimate. As you can see, the animate and inanimate are very, very correlate to the V1, which suggests that inside the category they might be using the simple features in order to differentiate. But when we go to between categories, the correlation is almost not existent, I mean, there is some correlation, but it's much less, which suggests that the IT is doing something more than just the simple feature. We can see it better in this graph here, which shows that if you look on the residual distributions over here, that for the V1, the inanimate and animate and between them got no different at all. I mean, they are both coming from pretty much the same distribution. However, when I look on the IT dissimilarity, I can see that somehow the category emerges from the data, which means that the IT actually did something that has something to do with that. So let's do the discussion.
Let's go into the discussion now. So first of all, we've seen that there is an inherent hierarchical category structures in the IT, but this actually been shown before in the monkeys. In the previous paper, they used even more stimuli, and they actually showed even finer categories. So this was already known, but we've already also managed to show that the same structure was both in human and in monkeys, which means different species. But more importantly, we've shown that it's possible to show it even when using different methods. And not just different methods, but methods that use different time scales of measurement and different temporal scales. That's like one we sample spatial. One samples single neurons, while the other samples 10,000s, 100,000s of neurons in each voxel. And since we could still see the same patterns and the same categorization, it may give rise to, it's possible that the representation in the brain has some scaling variance, or it's not just in like single neurons, or just also in the larger population. And actually another thing that they checked, which we didn't show here, but responds to what you said like previous, that there is no, they also showed that in the IT this categorization is not a result of single cells that are category specific, but it's a characteristic of the population coding of the IT, in the IT. So you have to check, to test the correlations between all the activity patterns to find these categories. It's something that's encoded, distributed across the neurons or the voxels. So this method of the RDM is really suitable because it leaves out the specific locations of each neuron or each voxel, and it only compares the statistics. So this way we could compare it, and also they also compared it to computer simulation to see if it's dependent on the log feature and so on. And that's basically the most like what we went over. They had some other there's some further discussion on about if this whole structure, what's the origin for it, if it's innate or if it's learned. And actually, by using these methods that are very short temporal, and the stimulus was shown just for 100 milliseconds or 200 milliseconds. So basically, it means that sorry, that's not innate thing, but that's also another thing that they wanted to say about the top-down or bottom-up processes. That it's mostly, as we said before, it's because of the short stimulus, it hints that it was more of a bottom-up process because there was no time for the top-down. And regarding the innate and not, the hypothesis, the main hypothesis is that the evolutionarily the IT was optimized not necessarily for the specific categories of innate versus animate versus inanimate, but more optimized to have the capabilities of being category specific, and then it's possible that these explicit categories were learned over time. And I think if there's any questions. Yeah.
Okay, thank you very much. Yeah, now okay, if you have any questions, yeah, we can have one or two. sum up the whole thing in 1 minute, okay, I think that the reason why I chose the last article is, first of all, I think it's a bewildering article in the sense that you use completely different scales and you get a similar result, as I think it's not something that you would expect. I think it also gives high relevance to the functional MRI because, okay, functional MRI, there's a lot of reason to suspect it. You're not measuring electrical activity directly, and you're still getting something which is scale invariant. That's something to keep in mind. I'm coming, as some of you know, some of you don't know, I have come from, single unit neurons and moved on to do work in functional MRI. Anyone who's interested in these methods, we apply them and others in our lab, so you're welcome. And another aspect which is really interesting, and we have not time to get into that, is the connection with behavior, right? So you think of these images, and you get the representation in inferior temporal cortex of the monkeys and the representation in humans. How is it related to the representation of our psychophysical experience? I mean, you could actually ask subjects to match these images and see how close they are, and now test the comparison between the behavioral representation and the representation that we have in cortex. So that's another level we did not get into. Okay, I think I took too much of your time. We'll cut it here. Thank you, and thank the speakers. Very nice.